Day 36, Honors Physics, Newton's three laws, problem number 4 and 5. So here's the initial diagram for problem number 4. There is no friction. We would like to draw a free body force diagram for each of the two different masses here. So I'll do that. So here's the full free body force diagram for each box. And I'm rounding off gravitational acceleration to 10 meters per second squared, so I can calculate the weights pretty easily. The weight of the 4 kilogram box is 40 newtons. It's pulling down, so then the table or the floor is pushing up with 40 newtons, because those will cancel. And then the big box is 60 newtons of weight, and then 60 newtons of normal force or floor force. And then the pushing force of 25 newtons, but the key here is the interaction force between the two boxes, and that's the only illustration here in this example of Newton's third law. The small box pushes on the big box with force F, and the big box pushes back on the small box with force F. They're equal forces, opposite direction. But they won't cancel because they're on two different boxes. Anyway, what we do is we apply F net equals ma to both boxes. So the small box, if we take F net equals ma, the result is the force 25 newtons, the bigger force, minus F, the unknown force, equals mass 4 kilograms times A. So we have 25 minus F equals 4A. Two unknowns, F and A. But if you look at the bigger box, you also apply F net equals ma. Here's the generic F net equals ma. Well, the only force acting on that box is F. So it's F equals 6A. So bottom line right now, what you have is a system of equations. You can solve this. I'll circle what we're at here. There's two equations. What I would do is I would take the 6A and plug it in over here for F. So you'd have 25 minus 6A equals 4A. Add the 6A's to both sides, you get 25 equals 10A. And you can then easily solve for A, for the acceleration. Once you have the acceleration, you can go back in then and plug into any of the equations to get the F. All right, let's set up part B now. All right, actually, number 5, it's like part B. But now we're pushing on the bigger box, in this case to the left. The leftward direction just happens because we picked the rightward direction in number 4. But we're looking for the magnitude of these forces. Once again, the same weights for each of the boxes. I've labeled my free body diagram here for each of the individual boxes. And I'm calling it F sub 2 now because it's different than the first case. I could have called that F sub 1 in the first case. So the big box pushes on the small box, F sub 2 to the left. Small box is pushing on the big box, trying to slow it down. And F sub 2 will be less than 25 newtons. But we do the same thing. We do F net equals ma. I'm not going to write down I will write down F net equals ma. You don't have to write this step. But I'm going to apply this to both boxes, come up with a system of equations, and then solve using algebra. So for the little box this time, the only force acting on it is F sub 2. So it would be F sub 2 equals m, that's 4a. Two unknowns. Same thing in the other box, but the bigger force, once again, this time is going to be the 25. So the rule that I use to take care of all negatives and to make the problem work out is take your big force minus the small force. We know that it's going to accelerate to the left. There's no friction, so the bigger force has to be 25. So it's 25. F net's going to be 25 minus F sub 2. They're in opposite directions, equals 6A. So once again, you have a system of equations here that you can solve using algebra. I would simply take the 4A, plug it in here, and you'd get 25 minus 4A equals 6A. And then you'd get 25 equals 10A, and then solve for A, plug in for A to get your F. It will be the same acceleration here because it's the same boxes with the same outside net force for the box system, but the force between the two boxes you might find to be a little different. Check it out.